Before a single line of software is written, engineers face a core structural problem: predicting the scale of an invisible digital architecture. For decades, the standard unit of measurement was lines of code, or LOC. You estimate the size of the final product by guessing how many lines of text it will take a developer to build it. Let's examine the data to see how this metric breaks down. Imagine two developers are tasked with building the exact same online shopping system. Developer A builds the system in C, resulting in a massive block of 90,000 lines of code. Developer B builds the exact same system using Python. It requires only 35,000 lines. Placed on a scale, the C program is visibly heavier. Based purely on this data, is the C program nearly 3 times larger than the Python program? No. Both systems deliver the exact same final product. Relying on implementation detail, the raw text, creates a mathematically flawed illusion of size. Both of these programs allow a user to log in, search for a product, add it to a cart, process a payment, and track their order. The client paying for the software and the customer actively using it are completely blind to the 55,000-line discrepancy hiding in the underlying architecture. A rigorous evaluation of software size cannot rely on text volume. It must focus entirely on the actual business functionality delivered to the user. To bypass this measurement failure, software engineers developed a strict mathematical framework known as function point analysis. This framework stops measuring how much code is written and instead calculates how much functionality is provided. It forces project managers to evaluate scale and productivity through the lens of actual utility. We can visualize this shift by looking at physical hardware. Consider this washing machine schematic. When evaluating capabilities, you look directly at external functions: wash modes, drying cycles, and automation rules. You do not calculate value by analyzing internal wiring density. Consumers judge the machine entirely by the tasks it performs. Function point analysis translates this hardware logic directly to software evaluation. Under this model, a function is a specific, measurable service provided to the user. A function point is the formalized unit used to measure those visible services. It ignores the programming language altogether. By counting function points, we establish a stable, universally comparable metric across any tech stack. It measures what a system does, entirely independent of how it is built. To calculate these points, we map how information moves. Here we have a central system boundary representing the application itself, surrounded by 5 distinct data pathways. Component 1 is external inputs, or EI. This is information flowing from the user into the software, like submitting a registration form. Component 2 is external outputs, or EO. This is processed information leaving the system boundary and returning to the user, like a generated digital invoice. Component 3 is external inquiries, or EQ. These are lightweight, bidirectional requests where a user retrieves existing information without triggering complex processing. Think of checking your bank account balance. Component 4 is internal logical files, or ILF. This represents the permanent, structured data stored and maintained entirely inside the software's own boundary. Finally, Component 5 is external interface files, or EIF. This is read-only data that the software uses, but which is maintained by a totally different system, like accessing a third-party payment gateway. These 5 data interactions are the sole mathematical building blocks used to calculate total function points. Modeling these 5 specific flows gives analysts a rigorous, objective map of the software's business complexity. Comparing these paradigms in a matrix, the differences are stark. Lines of code fluctuates wildly depending on the language. Function points remain perfectly static. Mapping their focus, lines of code isolates raw developer output. Function points isolate delivered business functions. This precision requires a practical trade-off. Classifying the 5 architectural components is a highly manual task. It is significantly more complex and time-consuming than running an automated script to count code length. Accurate function point analysis requires trained analysts. Relying on human categorization means two analysts might produce slightly different point estimates for the exact same system. It is a heavier analytical tool. Yet sacrificing the cheap simplicity of counting text lines is the mandatory price for achieving cross-technology accuracy. The most critical advantage of this methodology is timing. Look at this project timeline. You cannot measure lines of code until the coding phase actually begins. Function points, however, lock in at the very start of the timeline. Because it relies on defined user flows rather than source code, project managers can confidently forecast budgets and schedules using nothing but the initial customer requirements. To recall the core philosophy, engineers use the acronym FUNCTION. It focuses on functionality, is user-oriented, not language-dependent, and can be estimated early. Identifying the data flow is only the first step. To execute the actual mathematical calculation, we must assign complexity weights, simple, average, or complex, to each of the 5 architectural components. Measuring software size must align with the value delivered to the customer. By strictly counting what a system does, function point analysis provides a universally applicable, technology-agnostic foundation for modern project planning.